Everything after this discussion will no longer deal with batch reactors. We're going to start flow reactors on Monday, and we'll stick with those flow reactors for the rest of the quarter. What we're going to cover today is talk a little bit about what Matlab is doing. We've been kind of using Matlab as a black box at this point. I want to give you a little bit of insight into how it's doing the calculations it's doing so that it seems maybe a little bit less mysterious and also a little bit more obvious why particularly the ODE function file is written the way that it is. So maybe if you understand a little bit of how it's ticking up in time, it'll become a little bit more apparent why we're doing what we're doing, because when we switch to flow reactors, we end up using the same piece of code. If nothing else, by the time you're done with this class, you will no longer fear solving ODEs because you'll have written so many of these solution files, because most of the flow reactors require solutions of ODEs too. And in fact, very little of the structure of the solution changes except the name of the variables. Instead of time, we have distance. Otherwise, it's about the same. And then I'll also give you a couple of tips for how to write code on the exam. I have an example that we'll go over. Well, actually, we won't go over it. You will work on it. But this is a sample of an exam problem where you would have to write code. So we'll at least look at the structure, and you'll have an opportunity to work on it. We'll get to that after we do the Matlab bit. The exam 1 grades, the mean was a 31, which the mean is, C plus B minus range, which is right where we're headed. Keep in mind that the course itself is the thing that is curved. Individual exams aren't. So there's no curve on these grades, but generally that's more or less where I would like it to see, right? C plus B minus range is average. That's usually what we see, and that's right where our average is. So generally, I'm okay with that. So take a look at your exams, see if there's anything on there that was tripping you up. Pay particular attention. If you want to look at your exams and figure out, what do I really need to work on? If something on that exam has shown up on any of the recent 2 homeworks, pay close attention to it and figure out what you did. If it seems like, well, he was asking that just to see if I understand a concept, we're probably not going to hit those concepts again because they're sort of embedded in most of these problems. But if it was, I messed up my rate law a little bit, work on those rate laws because they're going to come up a lot more. Or if I left off a piece of my ODE, like I forgot an initial condition or something like that, pay particular attention to that because that would have showed up on the last 2 homeworks, because that's the sort of stuff that's going to come up over and over and over again. I mean, naturally, I want you to understand it all, but I understand that you also have other responsibilities, so if you have to prioritize, that's how I would prioritize. There is a regrade policy for the exams. It's pretty straightforward. You've got a week to take a look at your exam, go home, read over it, compare it to the solutions. If you catch a mistake, graders are humans, we make mistakes. Give me back your exam and a little written explanation of what the error was, or why what you wrote is still correct even though it was marked wrong, something like that. It can be pretty brief, about 2 to 3 sentences. If it's a simple addition error, like I got 28, it's supposed to be 29, something like that, no problem. Just make a little note of it, staple it to your exam, and hand it back to me anytime before Friday, in class, office hours, slip it under my door, whatever you need to do. But you've got a week to do that, so there's no rush. You don't have to scribble it out during class right now. I'm going to hand back the exams. They're color-coded and they are sorted in ascending order according to the last 3 digits of your PID. So when you look at this number up here, that's why the last 3 digits are offset a little bit. So look for your PID and your color, and it should be in there. So I'll just pass these around. If you don't pick up your exam, well, that's stupid, you're all here, so never mind. Well, in case you miss your next exam, if you check the box and you don't take your exam, I'll put it outside my office. If you don't check the box, I just keep it until you come find me. But since you're all here, you have the opportunity to get your exam. Any general questions? I know a lot of times when I come in here and I just start lecturing, it sort of seems like if you have questions, it has to be on the current material. Just because we're slightly ahead of schedule, does anybody have questions about what we covered or the course in general? Yeah.
So sometimes, like, I find it, like, in the actual function that I'm calling for the ODE, I'd like to, like, error check within that. How would I do that? Because it seems like I can only see, like, the variables and stuff that are going on, like, in the main file.
Okay, that's actually, does anybody have a laptop with Matlab on it? That's worth actually showing on the screen. Could I borrow your laptop for a couple minutes? Once that gets fired up, I'll show you a way to do something like that. Yeah. Oh, you got it fired up? Oh, he beat you to it. Uh-oh, now we're going to have a collision with that. You got one. Oh, wait a minute. No? No? Are these all Macs? Oh, good, you have an HDMI port. You're aware everybody's about to see what's on your desktop, right? You're good with that? I take no responsibility for whatever you see on this laptop. And actually, it's really nice that you.
I just want to.
Oh, now he's checking.
I just want to. No, it's fine. I just want to make sure no notifications show up. Oh, that's night shift. Yeah. Wait, what the fuck? Okay, never mind. You know what?
All right. If something happens, just yell and I'll unplug that cord real fast. All right, so a brief overview of how Matlab works. When Matlab is calculating something, there are two workspaces that are available. Actually, there are any number of workspaces available. You typically only see one workspace, which is called this base workspace over here. That's if I enter something from the command line. I need to pin this, make sure it's open. There we go. If I execute something from the command line, such as A is equal to, I don't know, some kind of a text. Right? What happens is that variable gets created in your base workspace and you can explore the value of that base workspace. If you write a function and run a function's variables are stored in what's called a function workspace. Typically, you can't see the function workspace. All you can see is the base workspace. So in terms of MATLAB terminology, what you're asking is there any way for me to look at the values in the function workspace rather than just what shows up in the base workspace? When we write our ODE solution script, I'm going to have to change your view here. So normally we would do something like t-span is 0 to 1, y0 is something, I'll just say it's 1. And then we would write t, y is ODE 45 at an integrand over t-span and y0. Underneath that is where we write our ODE function file, which looks something like this, and then along the way we need dy dt is equal to, I'm just going to say it's 2, or better yet 2 times t since we're about to do that, and then we would say end. So normally if I were to try to run this, it's going to ask me to save it. You have 2016b, which should be okay. So if you have an older version of MATLAB, maybe you need to put that function over in another file, which is fine, these tips still work. The way to explore what's happening inside your function to try to get an idea of, am I going in the right direction? For example, is my derivative with respect of temperature with respect to time positive or negative? Right? If I know it's exothermic and it's an adiabatic reactor, I should at least be able to evaluate the magnitude of that term. Or maybe I want to calculate my concentration at any time, right? It should always be positive. Maybe I can check that, something like that. The way to do that is through breakpoints. Breakpoints show up in what's called the breakpoint alley. So if your code is numbered 1 through 10, everywhere you have a code that you can put a breakpoint, there's a little dash right next to that number. If you click on that dash, for example, line 8, a little red circle pops up. That red circle tells MATLAB, when you get to this line, stop before you execute that line. Before it executes that line, whatever is available in the current workspace you're working in is going to show up over here. So I just ran that code a moment ago, and the workspace only shows t, t-span, y, and y0. It doesn't show dy dt. dy dt is sitting inside the function workspace. We can do something else. Let's try other functions like f is equal to 2 plus 3, and g is equal to y of 1 plus, I don't know, t, something like that. Right? All those functions, f, g, dy, dt, none of those are going to show up in the base workspace. But they will show up in the function workspace. And if you turn that little, now I need to save this. If you turn on a breakpoint like you have on line 10, and then you try to run your code, a couple of things happen. You have now entered the debugger inside MATLAB, so the code is paused. The reason you know you're in the debugger is this big red button up here that says quit debugging. You are currently in the debugger. The other thing that has happened is you now have a green arrow on line 10 which says MATLAB is telling you I'm about to execute line 10. If you want to know what's going to happen in line 10, you can look over in the workspace, and now you can see all those function workspace variables. So now I see that f was evaluated and it has a value of 5, g is 1, t is 0, y is 1. Right? These are the numbers that MATLAB is using inside that function workspace. If you want to go to the next step, you have two options. You can either click step, and MATLAB will just evaluate this one line at a time. So if I click step, it'll evaluate dy dt. And I can see it currently has a value of 0. If I keep clicking step, MATLAB will just keep stepping through. That's usually a problem because now it's going to step into the actual file that's solving your ODE. So usually we don't go quite that far. If we hit continue instead of step, it'll just run the code until it gets back to the breakpoint. Usually that's where I end up doing it, is I set the breakpoint right at the end and hit continue and watch how all the variables update as it goes through its code. So this is a way for you to check what's going on as MATLAB is doing whatever it is it's doing. When you're done, when you're all done with it, click quit debugging and then remove this red circle. If you click on the red circle, it goes away. And now when you click run, the code will run normally. If you have any red circles, it'll always stop at the red circle. That's the function workspace. Good question. Any more questions on that before I hand back the laptop? Yeah?
Can you please repeat how you saw the workspace inside the function?
Yeah, so the way that you see the workspace in the function is two steps. Step one is put a breakpoint somewhere inside the function. Let's say it's here. So you click on that little dash next to the number and you get a red circle. So step one is set a breakpoint. Step two is run the code. When you run the code, the MATLAB runtime behind the scenes will stop execution wherever you put that dot, and whatever workspace you happen to be in at that time is what's going to show up in the workspace over here. Yeah.
So when I was doing my last homework, I tried to do it. I've never seen this before, having your function in the same file as your main code. And it seems like you can't have more than one function in that. Is that true, or am I just
I think you can have as many as you want.
Oh, really? Okay. And then
in the newer version. So in the newer versions of MATLAB, you can now have local functions like this within scripts.
Okay.
Older versions of MATLAB, you can't put functions inside scripts.
Okay, and then for the handle on it, let's say that I did have a function in a different file type, when you're calling at integrand or whatever, is that calling the file name or is that calling the function name?
The MATLAB syntax rules say that those two have to be the same.
Oh, okay.
So if your function name is different from the actual name of the file,
yeah,
it should give you a warning that says you need to fix it.
Okay.
Yeah. Which is one of those cop-out answers, which is, it's doing this, which one does it do? Well, I don't know because it's never supposed to do that. I'm sure it does something, but I don't know which one it does because that's not supposed to happen. Any other questions? At least on MATLAB, before I give the laptop back. Okay.
survived.
Thank you kindly. Any other questions in general before we get into a little bit of what that actual MATLAB code was doing that we accidentally opened up right there? No? Okay. So it's a little unusual the way that we are attempting to solve these things, these ODEs. If we ever wanted to solve an ODE by hand, we have these analytic tools that will say, all right, if I can rearrange these into separable equations and then I can integrate both sides, then I can get the answer. MATLAB's approach looks a little bit different. If you're going to do the integrals, you need the same amount of information, but you also need to know calculus, right? In order to do those antiderivatives, you need to know calculus. The way that MATLAB is working is it only uses algebra. Somebody sat down and turned the calculus into a numerical approximation that uses only algebra, so that we don't need something like a symbolic algebra engine to actually do calculus. So MATLAB is solving your differential equations, which are calculus, strictly through algebra. The way that it's doing it, at least the workflow that we've seen so far, is that somehow we start with an initial condition and some ODEs. Right, you'll notice the questions on the previous exams were things like set up but do not solve the ODE. So somehow if we have just this much information, which is our initial conditions and our ODEs, we can dump this into a black box. That black box, I know, psychedelic, right? We input these into a black box somehow, and out comes all of our moles, I, as a function of time t, and anything else that we wrote a differential for example, temperature as a function of t. We'll see a couple more things. The most general one that we will see eventually is pressure as a function of t. We haven't really paid attention to pressure in batch reactors, but it will become important in flow reactors. And we haven't really talked about what's inside that black box or by what process that black box is providing these answers. All we know is that somehow MATLAB's doing it. MATLAB is our black box, which has something of the order of, step one is define your initial conditions and your ODE. Right now, step two is just kind of a mystery. And then somehow in step three, we profit from this. Right? We don't really know what MATLAB is doing. We know how to tell MATLAB what to do, but we don't know the routines by which it is doing the solution that we are obtaining. So generally, the numerical approach to solving a differential equation is to get really close. We can never solve these things analytically by the schemes that we're going to show here, but we can get so close that it doesn't matter anymore, right? For all reasonable intents and purposes, if we have 9-digit accuracy, we don't really care if that's not the exact answer. The way that MATLAB, or not just MATLAB, almost any approximation to solve a numerical differential equation, or numerical approximation to solve a differential equation, is based on the following. If we have something like dy dt, let's say that this equals 2t. That's a little bit tiny. Let me write that a little bit bigger in case you guys can't see that. So dy dt is equal to some function. It can be any function of y and t, right? We've seen that concentration can be a function of concentration and temperature. I'm just picking something simple that's, dy dt is equal to 2t. Our initial condition can be something like y of 0 is equal to 0. If we wanted to solve this exactly, we would need to separate and integrate. And we would end up with y is equal to t squared. That's the exact answer. MATLAB has no idea that this is the exact answer. Instead, what MATLAB does is the following. So MATLAB says, I'm going to approach dy dt, and I'm going to approximate that as the change in y over the change in t. So I've transformed from a differential equation to what's called a difference equation. The deltas here these are math deltas, not chemical reaction deltas. We're not talking anything about before and after reactions. We're just talking about the change in a variable with respect to the change in another variable. Matlab says, I'm going to approximate that difference in this way, such that if I want to calculate y new, right, the next value of y, the next value of y is equal to the old value of y, right? This is the delta part. If you expand out the delta y is y new minus y old, plus the derivative itself, dy dt, evaluated at some time t, times delta t. This should look something like a rate equation, right? When you remember the old expression, distance is equal to rate times time, the distance that we're changing here is where we end up with the new y value. We started with the old, so the real distance that we traveled was y new minus old. The rate at which we are changing is the derivative, and the time over which we're evaluating that is delta t. The big difference in almost all the solvers start out this way, right? This is the base case of how do I figure out the new value based on the old value. The difference is how different solvers evaluate this dy dt term and how they choose this delta t. Normally, we aren't the ones who are choosing this delta t, we're letting Matlab choose it. It has algorithms behind the scenes that say if delta t is very, very tiny, I'll get very good approximations here. Sometimes I need that, sometimes I don't. But we can approximate what this is doing pretty straightforwardly in the way that I've described it here, which is we can estimate the slope of y with respect to t at some time t because we have an expression for that slope as a function of t. So we can plug in our values as we go along. So for example, let's see how we would solve this dy dt is equal to 2t in a numerical approach, right? How could we estimate what that answer is? And as we'll see, the answer is not going to be great, but that's because we're doing just about the simplest approximation we can come up with. But all of the routines follow this same process. So we're going to come up with a table, which is exactly what Matlab is doing. We're going to start ticking up our time. Almost always we start at 0. That's time that we start. We're going to choose easy values of time, right? We're going to choose 1, 2, 3, 4. The difference here between what we're doing and what Matlab is doing is Matlab will choose those times based on how fast your variables are changing. Right? If your variables are changing very, very quickly, it will choose very, very tiny time steps. If they're not changing very much, like if you were to plot your data points when you reach equilibrium, you'll see the gaps between those data points get very, very large because Matlab knows those values aren't changing very much over a very long time. Then we're going to tabulate some values. So we're going to calculate the change in delta t. We're going to evaluate our derivative, dy dt, at whatever value of t we happen to be at. This, remember, according to the problem statement, is equal to 2t. Then we're going to calculate y as an approximation. We'll compare that value of y to the exact value. Normally, we're not so lucky that we can actually compare it to an exact value, but we have a nice toy differential equation here that we actually have an exact solution to. So remember, the exact solution is supposed to be t squared. So the very first line we can skip. Why can we skip the first line?
There's only an initial line.
Right, there's no delta that we need to worry about, and the initial condition itself says what that first value of y ought to be. So there is absolutely no difference in the approximate answer here, which is exactly 0. It is 0 because this is defined as the initial condition. Ever so conveniently, which is not really convenient at all, the exact solution has to give the same value. This is how Matlab gets started. It needs to know that initial condition so that we can start calculating deltas. So I'm just going to draw a little blank in here because we don't need those. So we go down to T1. And now we're just going to calculate each one of those values. So at delta t, we have increased by 1 second. dy dt says that we should multiply 2, because that's our little constant that we have. And our current time is 1. So we have 2 times 1 is equal to 2. The approximate value of y, this is now where we go back to the previous equation. The approximate value of y is this y new. So we're going to take our old value of y, the current value of the derivative, which is our estimate of the slope of the function at this time t, multiply this by however much time we let elapse, add those two together, and that should be our new value of y. So our old value of y was 0. Our slope at this point is 2. That's the value we just calculated. And our delta t is 1. All of this is equal to 2. I'm going to shift my exact values over a little bit since we're getting a little bit close. So our new value is 2. Our exact value is what? 1. Right away we can see a difference here. Our differential approach said I ought to get 2, and yet we know the exact solution says it ought to be 1. This is not at all unusual. Anytime you take a step away from your initial condition, you will not get the exact answer. There is no way for a numerical approximation to give you exactly what that is. The question becomes, how close do you think is okay? This is probably not very close. But nevertheless, that sort of an occurrence is pretty common. You will never get the same value from an approximation as you get for an exact function. So we'll talk about how to make that better in a moment, but let's practice that routine a little bit more. If we go on to time 2, the time step I took is still 1. The dy dt is 2, oh, no, don't cut, there you go, is 2 times whatever time it is, which is 2. So now we have 4. Our y approximate is the old value of y. The old value was 2. Plus dy dt, which is 4, times delta t, which is 1. All right, so I've sort of snaked in this value of 2, and it's shown up here. This value of 0 showed up here. All right, we're just taking the old one and adding on to it as we go along. So the new value here is 2 plus 4, which is 6. Our exact value is what? 4. So again, we're not dead on, but we've at least got a little bit of a pattern going here, right? It's at least going in the right direction. We can keep going. If we go down to time is 3, then our delta t is still 1. Our derivative is 2 times 3, which is 6. And our new value is 6 plus our derivative times the amount of time we've elapsed. So again, we're just carrying down that old value of 6. And so now we're at 12, whereas the real value should be 9. And just so that you can see the pattern, we'll go on to the next one. So now we've got 2 times whatever our current time is, which is 8. And now we've got 12 plus 8 times 1, which is 20. Write down, that's fine. Thank you. And so again, we're going in the right direction, right? But we're always a little bit off. Yeah, did I make an algebraic mistake? Oh, yes, thank you. So again, we'll talk about how to make that better in a moment. There's only 2 ways to do it. But this is the general approach that Matlab is using to solve these functions. Every time you go down a row here, that's Matlab calling your ODE function file. ODE 45, when you say, I want you to solve the integrand in my ODE function file, ODE 45 is going through each of these steps, and every time it moves a row down, it's recalculating what all your derivatives are based on your ODE function file, the one that you write underneath the script. The only thing that it needs to know is how to evaluate what your derivatives are. It needs an expression for the derivative, and then it makes some approximation to figure out what the new value is. And so if you do what we did before, where we're looking at the function workspace and evaluating those variables at every step, you're going to see basically this row of calculations every time Matlab goes through them. The general approach doesn't change regardless of how accurate you want to be. The two ways that we can improve accuracy, one of them might be semi-obvious from what we were doing in here. Can anybody catch it? Change your delta t. If you take very, very tiny time steps, you get better and better approximations of your derivative, right? Where we make this assumption down here. Remember, the definition of a derivative is when, well, roughly speaking, the definition of a derivative is when these two values approach 0, right? For not these two. Delta t approaches 0. You take a really, really tiny time step, and suddenly those differences look really, really close to the actual derivative. So the smaller the time step you take, the more accurate you will be. You can see Matlab taking these time steps when you do the plots of concentration or conversion or whatever. If you add the data points on there, you'll see they'll all be clustered right about at the beginning where everything's changing really fast. And then those data points will spread out because Matlab doesn't need quite as tiny a time step anymore. So there are two ways to improve this performance. Step one, or I guess option one, is to use a smaller delta t. That's one way to do it. The other way to do it is to approximate dy dt better. Right now, there's a key feature of this dy dt that we're evaluating, which is we are evaluating this dy dt only at t. There are other ways to get a better approximation of what the function is doing in that general area, because remember, I'm sitting at time point t, and I'm trying to project what the function is going to do into the future. If I only evaluate it this way, one of the reasons this is poor is because this approximation assumes that the function changes linearly into the future. Right? We have, when you see this expression down here, this is a linear function, right? There's nothing nonlinear inside there. It's a slope times a difference. So it's assuming that the function changes linearly. There's almost no reason to expect that functions change linearly, so you can change the way that we represent this correction term over here, which is why the numbers 4, 5 show up after the word ODE. So ODE 4, 5 is looking at what's called a fourth order correction for something like this. It's conceptually looking at up to the third and fourth derivative of this term to get a better idea of what that term should look like when it's projected into the future. There are many different solvers, right? I think I sent out an email that said if ODE 45 was taking you too long on one of those problems we had on the last homework, try ODE 15S. The S means stiff. If the problem is what's called stiff, there are multiple time scales where it's initially changing very, very, very quickly, and other times not so much. Sometimes standard solvers aren't very good at that, so you have to switch to a different solver. But all of the solvers have this same general feature, which is we start with some value, we increase time a little bit, and we estimate the new value of the function based on the slope of the function. If you can do either one of those better, you will get a better answer. ODE 45 is sort of the most general way to do that, or not most general, the most flexible way to do that. It works for the majority of the equations that we run into, which is why we use ODE 45. If you want to see the way that ODE 45 is approximating this dy dt term here, actually this entire term over here, you can dig it out of the documentation for ODE 45. There's a reference right at the bottom that says, go see this paper. You click on the link and a big equation pops up that says, here's how we're going to approximate this term. It'll have exactly this structure, which is y2 is equal to the old value plus some estimate of where the function was going. And that's how the majority of all differential equation, or numerical differential equation solutions proceed. All we need to know is where we started, and then we tick up this way. And eventually we presumably get to a close answer. And it is much more accurate than what we've demonstrated here, which is sort of the impetus for making better methods, because this simplistic linear method doesn't work very well. But the approach is the same for all of them. This, by the way, then, if you wanted to know how does this look in code, often our code looks something like time. We could have a delta t or something like that, but instead of dy dt, we would have something like dca dt. And remember, this is equal to our rates. I'll erase that for a moment. And then eventually we end up with a C sub A. So what Matlab is doing is saying, okay, I'm going to start at time 0, go up to time whatever. Actually, let's change these. Maybe instead of 1, it's something really tiny, like 1e to the minus 6. The next step doesn't have to be the same. It could be anything new. But you'll notice that the time steps get a little bit bigger as you go on. We don't set those time steps. Matlab will do that. What we do tell Matlab is how to get that derivative at any value of t, which is why we have lines in our code that looks like dca dt is equal to something like minus k times ca minus, no, there are no fractions in MATLAB, cb divided by kc. This is why we have lines of code that look like that in our MATLAB solution scripts. That's us telling MATLAB how to approximate that derivative. We have a function for it. It'll use its better, higher order approximations for how the function is changing, but we have to give it this general function for that slope at any time t. That's why we have code that looks like that inside of our MATLAB code. The rest of the ODE function file, remember these usually show up at the end of the ODE function file. Everything that's occurring before that is just so that MATLAB can plug those values into here. That's the only reason the rest of that is there, is so that we can evaluate this single term. Then when we wanted CA, that's what ODE 45 is doing. So this is the general structure of why we only need to know those differentials and their initial conditions, and roughly how MATLAB is approximating the true value of that function. Yeah?
Whenever we solve a differential equation, we don't need the initial conditions. We just need some value of y for any value of t, and compare what that constant is. Does MATLAB have to have the initial condition, or can we say this is what it is at the end, or some intermediate condition?
You can give it anywhere. It's just that the output is going to always start at time 0, but you can shift that time based on whatever your actual initial condition was. So let's say instead of CA at time 0 was 0 or 1, maybe you knew CA at 5 seconds was 0.5, right? Your initial condition that you would give MATLAB would still be 0.5. That part doesn't change, but now all your times get shifted by 5 seconds. It's also, you can't go backwards, right? You're always starting at that time. Any other questions? Okay. Oh, yeah.
Are we going to have to do this sort of approximation on an exam or homework, or is this just to help us understand MATLAB?
Just to help you understand MATLAB.
Okay.
Because we're going to, if, like I said, if nothing else, you'll be sick of writing this code by the time you're done with the class. But you'll also be confident whenever you see a differential equation that if I have to solve this thing, I know how to do it. Maybe it's kind of tedious because I need all this code, but I know roughly what the code looks like. And so if you're going to have that tool in your toolbox, I want you to have at least a general idea of what that tool is doing.
Okay.
So yeah, I'm not going to make you do any numerical approximations on the exam. So just a review of, I'm about to give you the example problem that we've got, which, again, we're not going to have time to actually solve it. I don't want to solve it in class. It'll just be an option or an opportunity for you to look at what these problems look like when they're on an exam. The general function form for any of these solutions comes in 2 parts, right? We always start off with this t-span is equal to something. We always have our initial condition y0 is equal to something. And then we always have our actual solution, which is t and y are equal to ODE 45 of all of the arguments of ODE 45. This was our ODE solution script. So whether or not you've been using the up-to-date version of Matlab, where you can put the next part in the same file or not, you always need the next part, which is the ODE function file. And that usually starts off as function, and we're going to figure out what the slope is. dy dt is equal to integrand, or whatever you want to name it. You don't have to name it. Integrand of t and y. So the structure of this function follows a particular pattern that I've tried to lay out, I think, 2 or 3 times in class now. And now from this previous discussion here of exactly how Matlab is calculating these things, we know we need some function that will tell us what this slope is for all of our differentials. And so these end up being the last thing that Matlab needs. All right, the very last line that you see in all of these is dy dt is equal to all of our rates, right, up through however many you have. By the way, on your exams, if you screw up a semicolon and a comma, you're not going to lose points because you have a minor syntax error like that. And then, of course, an end function. Ooh, I can color code this just like Matlab does. Oh, I can do function too. This is what chemical engineering for 15 years does to you. You get excited about stuff like that. So the overall structure of how this code executes has to follow the form in order to provide Matlab this information, in order to give it this slope. So by its very nature, you would do this in your head if you had to calculate this one step at a time. The very last thing that you can calculate is that slope. Right? The very last thing that you can get is dCA dt. Usually this is equal to something like RA or minus RA or however you want to write it. Right? In order to evaluate this, I would just have to move backwards and make sure I've defined all the terms that are inside there. So the next term up, I would have to say, okay, well, what's RA? So that Matlab knows what RA is. I'm trying to keep this as we would actually write it in Matlab. So here we would have, R sub A is minus K times, I don't know, CA. I'm just going to keep it simple for that. And so now Matlab needs to know, okay, well, what are my constants? Maybe my constant doesn't vary with time. So I would put my time up here. Maybe it's, my rate constant K is just 0.01. That's the general structure of whenever we're writing this code. If you're not sure where to get started, work backwards. Right? We know where we need to end up, which is dCA dt. Right? The most general equation that you can think of for dCA dt is R sub A. Or maybe it's the sum of all of the rates for A or something like that. Then you can work your way up and say, well, I know when Matlab gets to this line, it's going to have to figure out what RA is. So I need to give Matlab an equation for RA, which is this. Okay, well, when Matlab evaluates this, it needs to know what K and CA are. So I need to tell Matlab what K and CA are. So this is a pretty straightforward way of building up your code in reverse. And it always ends up with these 3 similar sections. Right, so the very last one are your ODEs. The ones that come before that are any of the equations that you've got. So when I say equations, that's things like adjusting things for temperature, or if you have to do a unit conversion or something like that, or if you need to express an actual rate up here, that's where your equations would come in. And then all the way up at the top are any of your constants. This tends to be the one that I spend most of my time on. It's fairly, when we see the differential equations, possibly with the exception of temperature, these differential equations for concentrations or moles all take on pretty much the same form, and they're fairly straightforward if you just write RA. Right? They're either RA or they're RA times V. Those are the only 2 versions of these material balances that we have. And then there's that form of the temperature one, which might take a little bit more. The constants almost always come from where? They got to be given to you, right? Or maybe you look them up with EQ Calc if you're doing a homework problem. On an exam, all the constants would have to be given to you. It's that chunk in between where if you're not sure, do I really know this material for an exam? Do I know how to code it? These equations should come fairly readily to you. So if you're developing your cheat sheet for the next exam, I would focus, well, not focus on it all, but pay particular attention to the equations. Because once you've got the constants up here, which come from a problem statement, these derivatives down here always take the same form. They're slightly different if you have the multiple equation version, or multiple reaction version compared to a single reaction. But if you want to be overly general, you could write a single script that can solve something for multiple reactions, and it would also be able to solve a single reaction. But those elements of the code don't really change very much. This part is called your ODE function file. Right, so hopefully now it's a little, you've already practiced it a lot, so no part of this should be particularly surprising. But the reason that they're there in the pattern that they are is because of how ODE 45 is approximating the solution to your differential equation. It all starts with needing to know what the value of the slopes are at any particular time, or any particular value of CA. Those equations change a little bit when there's more than one variable. But the reason we need to code in this structure is simply so that we can get a numerical value of this. If we can get that numerical value, ODE 45 will do the rest for us. And that's why this code is always structured the way that it is. So I'm going to hand out, I'm going to try to fire this up and maybe it'll work or not. I don't know. I'm going to pass around an example of what this kind of coding looks like on an exam. Actually, I'm also going to post this on TriTED, so if you have a chance. I have more copies that are going around. All right, so take a quick look at the way that this code is structured, because this is more or less what it'll look like on an exam. I know some of you don't have one yet, so just look at your partner. There will be a typical problem statement like we've got on all of the other exams, and underneath I am giving you elements of the solution script, right? I've given you the solution scripts up here that has T-span and why not ODE 45, and I've left some blanks in there, right? You would need to fill in what those blanks are. I've also typically will tell you what the variables are so that we're all using the same variables. And then you just get lines of blank area to work, right? One line of code each. There will be extra lines of code. You don't have to force everything into this. But if you flip it over, there's more and more lines that you can write on. Way down here at the bottom is that very last line, right? If I needed to know all those differentials, here's what it is. Immediately, this implies that I need at least one line for DCADP, all that kind of stuff. I probably won't give you 5 components on there to do, but nevertheless, this is what will show up on there. So if you're looking to practice something, I would practice something like this. This is going to be available on TED in a blank form. You can practice it with all of the previous homework problems that we've got. And you'll see that if you haven't noticed it already, they all take exactly the same form. So we're not going to go over the solution for it. I will post the solution for this at a future point. Yeah?
Would our why nots have to correspond with the why of one and also the difference of the
Yes. So the why nots always follow the same pattern.
Okay.
All right, that's all I've got. Jenna's got a problem session this afternoon, and then I will see you guys next week. Have a very nice weekend, everyone.